simplest wave is this is wave in one dimension. Let us assume this is a wave function psi, and psi satisfies the wave equation. What we learned previously, not in this class, but somewhere else already. This is wave equation. Tell me why it is a wave. What is the definition of wave? If it is a wave, its shape is the same and it translates. Sorry, I assume the two shapes are the same. It has been translated by Vt. So this is a function of f of x, and this is function translated by Vt to the right side along the x-axis. So this is function x minus Vt. Then this is just a translation, and the shape, the two shapes are the same, right? You do not agree? Okay, in that case, what happens? If I, let us assume that this function has a double derivative, then I can compute and what happens to the same spatial double derivative of x minus Vt. This is the same as this, substituting after taking the double derivative of f of x, then substitute x equals x minus Vt, right? And what's the second order derivative of this? Don't know. Sure. First order first. What's that? I can, let us call this one A. Oh. By using chain rule, I can write it like that. This is minus V. Am I right? Using the same way, this one has minus V squared. If I combine these two, they are the same except for this factor V squared. So if I substitute this one here, assume this is then that kind of function always satisfies this equation. Okay? But can you see any difference between the Schrödinger equation and this normal wave equation? This is second order in time, and this is first order in time. It's a little bit different. So in general, this equation may have real solution, but this equation, in general, it is expressed in complex wave function. That's the difference. Assume it is if we make use of the fact that momentum is a spatial derivative up to over a factor. If I take the derivative with respect to time, something, for example, in this case, if I introduce a sine or cosine, double derivative will bring the same function up to over a factor. But if I substitute sine or cosine here, time derivative will change, single time derivative will change sine to cosine or cosine to sine. But double spatial derivative will bring the same one, cosine to cosine or sine to sine. There's a mismatch. Okay? So Schrödinger equation is a wave equation, but that is in a little bit different from normal wave equation. Big difference. Okay, so first of all, we have a postulate momentum is proportional to wave number. What is wave number? What is wave number? Kx minus omega t is where lambda is the wavelength and t is period. Wave number is 1 over lambda, right? Frequency is 1 over t. So k is 1 over lambda. Kx, k is, what is k? I'd like to read out that momentum from the wave function, and we begin with the wave function, pre-particle wave function, which is similar to sine or cosine in complex form. And we remember that e to the I theta equal cosine theta plus I sine theta. So why don't we introduce e to the I kx minus omega t? So as a trial solution, I'd like to make use of exponential instead of sine or cosine. In that case, second order derivative will be proportional to exponential again, and first order will be proportional to the exponential again. That is different from choosing either cosine or sine. So, before doing that, let us classify what's going on here. Assume this is just trial wave function. We are not rigorous at all, however, just mimic. So using this trial wave function, let us see what happens if I do this kind of operation. IH bar time derivative will bring the overall factor minus I omega here. So it's h bar omega. It seems to be this operator has an eigenvalue of h bar omega, right? And this seems to be an eigenfunction. This shape of the function is the same, and after this operation we get the energy. The E equals h nu comes from the energy So this is h bar and this is omega. We begin with the energy of the photon, right? And we would like to copy the equation of photon's energy to usual matter. For example, electron or something like that. So if I want to read out the energy of the particle, what I'm supposed to do is just take the time derivative and attach some appropriate complex number. Okay. And then, what's next? If I want to read the momentum, what should I do? Take the spatial derivative of this function. Assume this is a 3-vector scalar product. Then what happens? Then I have ik vector and exponential I kx minus omega t. Right? But I have another assumption that momentum is de Broglie's hypothesis is what? H over lambda, right? This is h bar, this is k, right? So k is proportional to the momentum of a particle in quantum theory. So what I'm supposed to do to get momentum p as an eigenvalue is what? Multiply minus I h bar here. Then I get momentum p all right. So I think this can be interpreted as an operator that reads the energy of this free particle wave function. So we identify this operator to be Hamiltonian, and we identify this operator to be the momentum. And actually this is an operator. After acting this operator to the free particle wave function, then I get the eigenvalue as the number, vector, 3 vector. Okay, that's it. Then what I get is, if I act this one to the wave function, what I get is energy, right? But this is operator, so I have to put something to let this operator to read the eigenvalue, that is wave function. That's it. So, comma, h equals IH bar, and momentum p operator is minus I h bar. If you assume this is it to be a free particle. Okay? It seems to satisfy the free particle equation of motion. Free particle's energy is this guy, right? There is no potential energy and only the kinetic energy is there. So this equation, this classical mechanical equation can be written in quantum form like that. And then we extend this idea. What happens if the Hamiltonian is composed of kinetic energy and in addition we have potential energy? Then just extend this idea to the case H equals in configuration space, this potential can be a simple function, and this is an operator. And if I make use of this operator, what I have is something like that. That's it. Let's see, next one, equation 2.2. What happens to the probability? Schrödinger equation has the form and if it is a free particle, if it has potential, then we may have potential V, but let us consider simple case. And all right, I'm interested in what this psi means, and this is a way. Multiply psi star to the left hand side, or dagger, in case this is a column vector. You know, this psi can be expanded in series, and we have various states that make a complete set that we call them bases. So in that case, it can be understood to be a column vector has many states. They are all independent, orthogonal to each other. All right. And then multiply this. Oh. We have a equation. What happens if I take the complex conjugate of this equation? If I take the complex conjugate, Hermitian conjugate, complex conjugate, they are the same. if you finally have a number, then Hermitian conjugate is the same as just the complex conjugate.
근데 지금 저기서 psi가 저게 컴포넌트를 갖는 컬럼이면은 해밀토니안에 psi가 어플라이 된 거는 전체적으로 매트릭스인 거잖아요. 그러면은 Hermitian conjugate로 해야 되잖아요.
Let's see.
아니면 그냥 인덱스.
First take the complex conjugate because they are equal already, right? And then I have minus IH bar right? But I cannot compare this directly with this, right? To make a similar form, I have to take the transpose if I assume this one is composed of column vector. And then I take the transpose. Then this is what? Right? Now we can multiply column vector to the right side, right? And subtract. One minus two. Then if I subtract, then the sign will be the same. And where is it? Okay. We have the same sign in here. I have to subtract. So they can be expressed as a simple form. And this one can be interpreted to be divergence of this guy. Right? Because everybody knows, right? Difficult?
No.
So let me multiply, let me divide this one in both sides, and then and move to the left hand side. Minus. All right. What's that? I can interpret this one to be a momentum operator acting on this, right? Right?
그냥 아이가
Sorry? What's wrong? So, plus divergence of momentum operator acting on this guy, and plus, now it is plus momentum operator acting on this one, and am I right? So this is something like divergence of
그레이디언트 그 그레이디언트 사이에 퍼미션 컨주게이트를 디파인을 해야지 될 것 같은데.
왜?
헷갈릴 수 있는 게요.
minus IH bar minus 1 plus IH bar operator P so it is something like two times the real right? So it approximately, it seems to be proportional to the momentum, real value of the momentum up to over a factor. I don't know what psi dagger psi means yet. And momentum divided by 2 cancels mass, something like velocity, right? It seems to be proportional to the velocity of an object in a classical sense. And finally, if we interpret this one to be probability density, not probability, just the density, then what we can say is something like density plus divergence, density, velocity equals 0. So it is continuity equation. So this one can, if we can interpret this one to be a density, then it has the meaning of current. So it's not a bad idea to interpret this one to be some density. But we remember in quantum mechanics, we declare that this is the probability density of finding a particle at some point, right? Where probability is just the rho times the dx cube integrated over some volume. Then So by computing this kind of way, we find that the psi dagger psi it is reasonable to treat this guy to be a probability density, and it is also reasonable to interpret this one to be the current. Okay? And in this case, we find that this one satisfies the continuity equation. But if we substituted some potential, here we consider the free particle case. If we consider the potential, if it is real, it satisfies the same equation. But if the potential has an imaginary part, that's different. We have some different result. The probability changes. Okay? It is possible to allow the complex potential, but as soon as we introduce the imaginary part of the potential, then we get change in the probability. In some cases, the probability decays. In some cases, the probability increases. Okay. That is the basic idea to construct the Schrödinger equation. But we would like to follow the very similar way to construct the relativistic equation of motion for free particle. That is called the Klein-Gordon equation. Our goal is the construct equation equivalent to the previous case, energy, free particle case. Energy is just p squared over 2m in the non-relativistic case. And relativistic case, we have energy squared equals momentum squared plus mass squared. I'd like to construct the equation that satisfies this eigenvalue equation using free particle wave function. Okay? And we have E equals h nu, that is h bar omega, and we remember that this is originated from the photons theory, and photon is already relativistic. That's important. So we don't have to modify this energy part. Photon is already moving with speed of light, and this formula came from that fact. But in this previous case, for the non-relativistic theory, we jumped up. We made use of the relativistic equation for the photon, but we applied to the non-relativistic particle, that is electron, right? So anyway, it is safer to apply this energy replacement by IH bar. Okay. And we have momentum H bar K, and it was minus IH bar. Oh. This kind of replacement was made in the previous case. I'd like to check what happens if we just substitute this one to here. Substitute. Squared equals momentum squared. If I want to be more accurate, then I have to put c squared, c to the fourth here, right? That's correct expression. So for the time being, for a few lines, let us revive speed of light. Okay, E, that's correct, and then PC squared plus m squared c to the fourth. Okay. If I square this, I have minus h bar squared double time derivative equals, sure, I have to put some wave function that must satisfy this. Here I have minus h bar squared c squared spatial derivative squared, and then plus m squared c to the fourth power. We remember x0 equals ct, so it's better to multiply c squared in the denominator to make it simpler form. Okay, let me just move this left hand side to the right hand side and then divide the whole equation by c squared. Then I have h squared, c squared, minus h squared, del squared, and plus m squared c to the fourth with some wave function. And because we want to construct a relativistic wave function, it's better to use a CTX. Squared. Okay. I can pull this h bar squared out. Then I have why don't we divide both sides by h bar squared? Then okay. By the way, we already have obtained some what's that? This is right? Right? And we remember they are different. Okay, so I can rewrite this guy, and this is what? Plus, minus, right? Oh, not zero. So, aha. Lorentz invariant operator. So equation of motion is simplified to be okay. So because our knowledge on the non-relativistic theory may work or may not work, why not trying with the previous result? For the free particle wave function, I have kx minus omega t. Let us rewrite this one, if it is useful or not. Let me just multiply h bar here to get the energy and the momentum of a particle. Then I put h bar in the denominator and have h bar k dot x, h bar omega t. Aha, this is h bar I p x minus e t, and this one can be written as a e over c times a ct, right? What's that? This is, if I pull this minus sign out, what I get is c e over c ct minus p dot x. That is e over c p dot ct comma x. That is actually e to the minus I over h bar p mu x mu. This is Lorentz invariant quantity. It was already Lorentz invariant. Or simply we just write it as p dot x. Without vector notation means it is just a scalar product of two full vectors. Aha. Last step we need is whether this guy satisfies this equation or not. if it really works, then we can make use of that one as a solution for this free particle wave equation. Okay, what's that? Down is up. The reason is that if I take the derivative with respect to this contravariant variable, remaining piece is coefficient of contravariant variable is covariant. So P alpha x alpha, then the result is and this is the same function. What's that? This is 1 only if alpha and mu are the same. Right? Therefore, it changes the subscript So using this result, if I multiply IH bar here, that is just P mu.
I don't understand from the second to third. What do you do?
Here to here?
No, second to third.
Second to third? Okay. This is f of x, something like that. F of x g. What's that? Chain rule. G is exponential. F is because you wanted to make use of this one P mu x mu. This one may work, but this is more general. For example, where A is constant, then this is xj, aj, and A is a constant, so I have this is delta ij. It is 0 if, for example, this is x and this is y, then it's 0. It is non-zero only if the two indices are the same. So the answer is AI. But here we have, because this is a Minkowski space, there is a metric tensor appears instead of delta ij. That's the difference. Now we understand this is covariant derivative. What happens to the contravariant one? You will find that this is you can do the same job to find that this is contravariant. So finally, we used to have this kind of operator. And let me just put this guy. Oh. If it gives over a factor exactly 0 or not, then what's that? It is minus h bar over I p mu minus h bar over I over h bar p mu and plus m squared c squared over h bar squared okay, this is minus p mu and h bar squared plus m squared c squared okay. So here we have m squared c squared subtracted by p mu divided by h bar squared. Okay, p squared is m squared c squared, right? If you consider the dimension, p is mass times velocity, right? And until now, we have been neglecting the speed of light. So in previous case, we usually write is p squared m squared. But in this step, we just kept all the c factors. And this is momentum squared. So we should have m squared c squared. It is exactly 0. So it seems that this guy seems to be a free particle wave function. And this one seems to be an operator that reads the momentum. Momentum p mu can be read. But do you remember what's the difference between this exponential function and sine or cosine? Sine and cosine are not the eigenstate of momentum. That are eigenstate of energy. They are composed of linear. They are composed, for example, sine p dot x over h bar. That is what? 1 or 2i e to the I p dot x h bar minus e to the minus I p dot x h bar. Right? They are linear combination. They have an equal probability of having the positive direction and negative direction. Just like the case we consider the infinite potential well, we have some solutions sine n pi x over L with various states. That case, this guy includes the wave that is traveling to the right, traveling to the left, because it is a standing wave. Standing wave is composed of equal rate of two waves, to the left and to the right. So they cancel to shape. It looks, does not travel and just standing somewhere, up and down, not moving, because of the fact. But in this really free particle, the equation, the solution that is complex instead of real, that is always moving either to the right or left, because it is a momentum eigenstate. That's another difference. Even though the equation, this one is both of them are solutions of the wave equation. Okay? All right. And more interesting thing here is that these operators is four-dimensional. They are transforming in a covariant way. So what we have found is that, let me just neglect all the speed of light and h bar. This is the equation of motion for the free particle. Relativistic equation of motion for free particle, and that is Klein-Gordon equation.
H가 C는 다 1도 넘는
We return to our particle physics. But if you want, you must be able to revive all the factors of C and h bar. If you understand, you have to remember kx minus omega t. That's the most important thing. If you remember this, you can bring in all the h factors in a correct way. I will write everything from now on. I will just write minus p dot x. I won't write h bar anymore. I won't write c anymore. So if I write e to the minus I px, that means it is p over h bar. Remember that there is no c's in here, in the argument of exponential. C appears where? C appears when you interpret this one, because P is momentum, you will have to remember the dimensions of mass, but if you write this P that is a momentum, so you have the dimension of velocity in addition to the mass. So what is, count the number of velocities, then put such a number of C's. That's fine. Okay? So next step is we are inclined to interpret this equation of motion, whether it satisfies some continuity equation, so that it can, the previous result for the Schrödinger equation can be generalized to the Klein-Gordon equation, right? Is it still psi star psi, the probability density, or is it still the derivative applied to the wave function with the momentum, and that is proportional to the current, so that it satisfies the continuity equation? That's our next job, right? That are all given on page 25 and 26. And I believe you can do that. But I can comment about something regarding the continuity equation. So here, C is missing in order to make it in a covariant form. Let me multiply 1 over C. Right? Just count the dimension. This is length inverse, right? And this one has the same. This is current, this is density, and current is usually density times velocity. So we have velocity dimension one more, but it is cancelled by the speed of light, so this is correct. So I'd like to make this equation to be re-expressed in a covariant form. Haha. With negative sign in here. It's confusing. Just okay, this is round 0. Okay. Sorry about that. I had better multiply C here. 0. That's better. And do not divide both sides by C. Okay? Zero plus, actually minus dot J. Right? We remember upper one is and this one is 0 minus J. Right? So this they are just up contravariant and 0 this is the same, right? 0 minus J, that is J mu, right? So it is Lorentz invariant form. So continuity equation is already Lorentz invariant. This form must be the same everywhere, as long as if you are writing the equation in an inertial frame. So by accident or fortunately, we were ready to study the relativistic wave equation. Thank you.